We are in section 4.5 on page 8. The example says sketch the graph of f of x equals x to the 5/3 minus 5x to the 4/3. So the first thing is, what is the domain of our function? And since we have cube roots here, if you were to rewrite this in root form, our domain is going to be all real numbers. Next thing is, do we have any asymptotes? And then also, what are our x and y intercepts? So we have no asymptotes. This is not set up like a rational function. And then next, we have our x-intercept. X-intercept is where y is equal to 0. And when y is equal to 0, we have 0 equals x to the 5/3 minus 5x to the 4/3. I'm going to move my 5x to the 4/3 to the other side. And then I'm going to raise both of these to the third power. And when I do that, I get 5 to the third, which is 125. X to the fourth equals x to the fifth. And moving everything on one side, I get x to the fifth minus 125 x to the fourth equals 0. Factoring out x to the fourth, that means that I have two x-intercepts. I have one that's at 0, and my other one is at x equals 125. So I'll write those as ordered pairs of 0, 0, and underline it so I can find it easy. 125, 0. Next thing is for my y-intercept. This is where we make x equal 0. And when we make x equal 0, we have y is equal to 0 to the 5/3 minus 5 times 0, which just be 0. So 0, 0. So our x-intercept and our y-intercepts. Next thing on our list is to figure out our critical values. So we need to take a first derivative. And our first derivative is going to be 5/3 x to the 2/3 minus 20 over 3 times x to the 1/3. And we have to take this and we're going to set this equal to 0 to find our critical values. And when we do that, I'm going to do exactly what I did over there with the intercepts, and I'll move this as 5/3 x to the 2/3 equals 20 over 3 x to the 1/3. I can multiply both sides by 3, and 5x to the 2/3 equals 20x to the 1/3. And then divide both sides by 5. I have x to the 2/3 equals 4x to the 1/3. And then from here, I'm going to go ahead and raise this to the third power on both sides. And so we have x squared equals, and we have 4 to the third, which is 64, x to the first, and then moving everything to one side, we have x squared minus 64x, and we can factor out an x. We have x times x minus 64 equals 0. So we have two critical values. Those are going to be at x equals 0 and x equals 64. And where do we have any places in our derivative where we have the derivative is undefined? And no, there's no values where we have the derivative is undefined. So these are our only critical values that we have. So the next thing that we're going to do is find our possible inflection points. So we're going to go ahead and find a second derivative. So our second derivative is equal to, and taking the derivative of our first derivative, we're going to get 10 over 9 x to the negative 1/3 minus 20 over 9 x to the negative 2/3. And you can rewrite this Let's do that first so we can see where it makes it a little bit easier for us to see where this function would be undefined. And so we have, since it's negative, it goes into the denominator, so it's going to be the cube root of x minus 20 over 9, the cube root of x squared. And solving this to find my possible inflection points, I set this equal to 0. I can multiply both sides through by 9 and also divide by 10. And then I'll move one of those terms over to the other side. And when I do that, I get 1 over the cube root of x is equal to 2 over the cube root of x squared. And from here, I'm going to go ahead and cube both sides just like how we did before. So we get 1 over x equals 8 over x squared. I can cross multiply here, and when I do, I get x squared is equal to 8x. And then moving everything over to one side, I have x squared minus 8x is equal to 0. Factoring that x out. And we get our possible inflection points are at x equals 0 and x equals 8. And then if you look back up at the second derivative that we had at the very beginning, are there any values of x that make our second derivative undefined? And yes, we do. That is at 0, when we already have that one as our possible inflection point. So next thing that we're going to do is we're going to take all of this information and we're going to make a single number line. And our domain, again, was all real numbers. So I'm going to take my number line, and again, all real numbers. And I'm going to break this up based upon my critical values and my possible inflection points. So my critical values that we had are at 0 and 64, and our possible inflection points were at 0 and at 8. And so we have 0, 8, and 64. And then I'm going to substitute these in a value in each of these intervals into my first derivative and my second derivative. And again, just like we did before, I'm going to split this up a little bit so it makes it a little bit easier for us to see those values. And if you want to pick something, again, we talked about the fact that you don't need that actual number, but if it helps you pick something less than 0, say test -1, and substitute that in. Something in between 0 and 8, you can test 1. Something between 8 and 64, test 10. And then something larger than 64, you can test 100. It doesn't matter, it's whatever you guys want to do. But we are looking at the sign. So if you look back up at your first derivative that we had, and I'll box it up here, and you were to test -1, and you substitute that in, when you do, you will get a positive value, and that means that because it's positive, that function is increasing. Likewise, if you were to test 1 in there, you will get a negative value, and that means that it's decreasing. And then substituting in 10, it is also decreasing. And then substituting something larger than 64, we get that it would be positive. It's going to be increasing. I want you guys to realize that at 8 was not a critical value. 8's a possible inflection point, meaning that your increasing and decreasing intervals should not be changing at 8, and it doesn't. Okay, from here we're going to do the same thing with the second derivative. And the second derivative, you can either look at the negative exponents or you can look at the roots. So either one of these. I'll box the second one. You can also look at the one right above it. And so again, testing those values is this time in the second derivative. When you substitute those values in, for the first one, when I substituted -1, I get that it's going to be a positive value, and so that means it's concave up. Substituting in 1, we get concave down, it's a negative value. And then substituting in 10, we get a positive value, which means it's concave up. And again, check those on your own. And then the last interval, testing 100, we get a positive value, so it's concave up. Again, I want you guys to realize your possible inflection points, which means where it could change concavity, is only at 0 and 8. So it makes sense that at 64 it's continuously concave up, because that's not where we would have any changes in concavity. So next thing that we're going to look at is, do we have any places where we have a local maximum or a local minimum? And so we have it going from increasing to decreasing. And then it changes again down here at 64 from decreasing up to increasing. So we have a local max at, and our maximum is at 0, f of 0. And we'll figure out that value. And we've actually done that already. So we have a local max at 0, 0. And then we have a local minimum at 64, f of 64. We'll work that one out too. Possible inflection points that we had were at 0 and 8, and then are any of those inflection points? And yes, if you notice, it is changing concavity at 0, and it's also changing concavity at 8. So our inflection points that we have are going to be at 0, f of 0, and at 8, f of 8. So getting those values, those points calculated. The next thing that we are going to do is look at each of these intervals and figure out what the shape of the graph should be looking like. So we have concave up and increasing. Should be something along these lines. The next one that we have is concave down and decreasing. The next one that we have is concave up and decreasing. And then concave up and increasing. So now that we have all of these values, next thing that we need to do is plot our points, our intercepts. We have no asymptotes in this one, but figure out if we have these points on there and then connecting them using the curvatures that we have from our sign chart up above. And so our inflection points are at 0, 0, and at 8, -48. And our local minimum is occurring at 64, -256. So we have some values in here, and again, I'll underline these so we can easily plot those. These values, we're going to go ahead and put these all on our graph. I want you guys to realize we are dealing with some larger numbers here, so clearly counting by ones would not be practical. So I am going to count by, on my x-axis, I'll count by, we'll do 50s or 25s. So this would be 50, and then 100, 150. And then for my y-axis, I'm going to count a little bit larger because we do have larger values there. And we'll go ahead and do counting by 100. So negative 100, negative 200, negative 300. So once you have your graph figured out, we're going to go ahead and plot all the points that we know. And we do have, back up at the top, we had two x-intercepts. One was at 0, 0. So I'm going to go ahead and put a point at 0, 0. And then we also had another point at 125, 0. So 125, 0. Okay, then we also had, back up at the top, above, we had a local minimum and a local maximum. Local maximum is at 0, 0, and local minimum is at 64, negative 256. So do your best in graphing that point. So 64, negative 256. And we also had an inflection point at 8, negative 48. So again, doing the best that you can. From here, I'm going to use my sign chart that we had and go ahead and put those curvatures in. So from from 0, we have that it is concave up and increasing. And so I'm going to go ahead and draw that in. Again, the exact curvature of this is unknown. The next one is concave down and decreasing. So it's hard to kind of draw in there, but do the best that you can. The next one is decreasing and concave up. And then from here, it's going to go up. We do have an x-intercept here, so I'm going to make sure I hit that, and it is concave up and increasing. So drawing that in, that is my graph. Again, double checking to make sure you got all your values on there correctly.